All right, let's get this party started. This is going to be about innovative and novel ways of integrating community systems together, which is actually one of the core attributes of ESIP, is the ability to enable that kind of thing. So what we're going to look at is some different methods of doing that. First speaker is going to be Dave Blodgett, talking about the second environmental linked feature interoperability experiment.
Also known as selfie. All right, so thank you for coming along. This work is still cooling, if you will. We've been working for the last 7 weeks on and off, face-to-face, on international collaboration on this project. And what I'm here to present to you today is largely stuff that we were working on yesterday. So it's exciting. This is a really exciting project for us at the USGS, and everybody that's working on it, I think, sees just an incredible amount of potential. So, okay, so what we're defining in this project called Selfie is an information model that's really a resource model in the sense of a uniform resource identifier or locator. And the big assumption we're making with this resource model is that we need community organizations to help us track information that is quote unquote about real world things. And when I say a real world thing, I mean something like a river, or a jurisdiction, right? Like a state or a county is a real world thing. In the sense that you can't get a river to come through your screen to you, right? But you can get the information about a river to come through your screen to you. And so when we assume that we need community systems that can help us track information about real world things, we need to basically start to design, and so we need to figure out what the architecture is for that, right? And the architecture needs to allow us to have common reference identifiers for real world things that everybody uses, and then the community systems are able to, maybe through a registration process and a crawler or kind of harvesting process, go out and find information that's about the real world things that the community systems maintain references to. And so the diagram I have on the screen here is something we've worked up basically this week as kind of the master architecture diagram. And this will evolve over time, but this is useful for the sake of discussion. But we've basically broken our resource model into 3 tiers. This idea of a non-information resource, which is like I've been talking about, it's a shared identifier for a real world feature, a thing in the world. And that thing, if you were to put it into the URL bar of your browser, you would actually, like a DOI does, you would get a redirect to a web page about the real world thing, right? And that's what we've been referring to here as a meta resource. And the key with the meta resource is that it's a set of statements about the real world thing. It's a set of it's the knowledge that the community system has about the identified thing, right? And the other way to think about it maybe is it's the set of it's a set of outbound links that say here's something about the real world thing, here's something else about the real world thing, from a whole bunch of organizations that hold information about it, right? Additionally, the meta resource is a place to encode really useful information, like what is that thing related to? And so in river networks is where I work most of the time. So what's the next downstream river, right? What stream gauges are on that river? What river or what aquifer does that river's base flow come out of, right? So these associations with other real world things are the content that you might encode into this meta resource, right? And then below that, you have your data resources, right? And data resources are typically going to be what we might think of as a representation of the non-information resource. But there's a whole richness of data resources that you might want to link, especially when you get into observations that are either of the real world feature or made by the real world feature in the case of, say, a stream gauge or some sampling, quote unquote, sampling feature. So that's the basic architecture, and the key, and where I kind of started with this discussion of the community system, is that at the data tier, there should be references back to the non-information resource, so that when a community system that wants to harvest and crawl data resources to discover what is related to real world things, they can discover those links and build the meta resource dynamically, right? So that we can have this living, growing knowledge graph that connects data resources to non-information resource identifiers. Okay, so that's the gist of it. There's a lot here. There's a lot of different pieces to this technically. We're really building on the technology stack that's been pushed in the for lack of a better term for it, the schema.org space, but it's really the JSON LD space, the linked data with a small LD space. That's where we're really working, because we want to kind of strive for really focused and simple solutions that are immediately adoptable by kind of any script kiddie, if you will. Anybody writing a JSON app, JSON script, or a JavaScript app should be able to take this stuff, find it useful immediately, and not even really realize that there's a rigorous set of standards behind it, right? That's one of our big goals. So I guess what I'm gonna share next is a few demos just to show what I mean by that, right? How are we actually going to achieve this really simple, approachable solution to the kind of resource model and the problem that I've been illustrating. And I'm to 1020, is that right?
Yeah.
Okay. All right, so the first thing I want to show is if we go to Google and search for an aquifer, you can see this result here has aquifer system Richelieu, and the URL is this geoconnects.ca/ID. And if I go to this, you may not be able to see it, and I can't actually blow this up, but I got a 303 redirect from that URL that Google had indexed, and it brought me to a different web page. So that ID was actually an identifier that our colleagues at Natural Resources Canada have minted for the Richelieu aquifer itself. And they're starting to build, this is a total pilot system that we're building in cooperation with our Canadian colleagues and this project, Selfie project. But this system is meant to be that community system that would track the links to information about the non-information resource. And what I find so cool about this is that Google, which could not have gotten a web page from this ID URL, they only ever got a 303 redirect, found the information on the info page, on the meta resource page, and they indexed it appropriately as at this identifier URL, right? Which is great. That means we can expose these non-information resource URLs in this architecture, and the mass market search infrastructure is going to pick those up and use them the way we want them to, right? As direct identifiers for something that isn't actually available at that URL. We don't actually know. I mean, we don't know exactly what that crawler's doing. You know, that I'm sure somebody has logs to say whether they, use content negotiation to get, there's a JSON representation of this page, right? The HTML in this page also has the JSON LD in the script tag in the header of the file. So we don't know exactly what they're using, but we're following best practices. Spatial data on the web best practices at this point, the W3C's data on the web best practices is behind all this, and it's working, right? So that's cool. Okay, so I'm not going to dwell there. The next thing that should have come up. So we're doing this on the US side of the border too, and this is just a quick kind of demo if this works. The network has been, yeah, okay. So I just clicked on the map, and this is an app built on the US's version of this app. Okay, so I deployed the same app on our side of the border, and what you're looking at here is it's a collection of meta resource pages that have been returned and rendered into an application. So this is just a representation of what we can do with this linked data kind of ecosystem, right? So we have this, I clicked on a watershed, and we can see, let's just see if any of this is going to work. There's one thing I want to show you in here. Okay, so I just clicked on a link to another non-information resource that this app went and looked at the meta resource page and found a geometric representation of. And I was able to add that geometric representation to the map, which, yeah, you can see that okay up there. I could go to the outflow of it. So I just clicked the linked data for the outflow. Let's see if some of these map geometries are, this is on very test infrastructure and not everything works perfectly, but what I really want to go and do at this point, so I just kind of showed, I got that piece of the demo. The real point was, look, we can follow the network of linked data. We can find other non-information resources and the data that's available for those other non-information resources. Cool, right? That opens up all kinds of potential. And this is all based on the technology that I've been talking about so far. So the last thing I want to show is, at least on this demo, this part of the demo. Okay, so we can follow the network. So here we're at a Nexus, which is a confluence essentially. We can go to the receiving catchment for this Nexus. At least we should be able to. Live demos, internet, always fun. And my servers are not happy. All right, so now we can go to a lower catchment, a lower catchment, a lower catchment. Now we're in Lake Champlain, a lower catchment. Now we're in Canada. So these linked data systems can be they can be governed as they need to be, and we can expose the edges of the linked data systems to each other. And we can now crawl these networks of interrelated features that happen to have relations to each other. And it doesn't have to be spatial crawling across these systems. It could be from a groundwater-oriented system to a surface water-oriented system. It could be from an aquatic biology system to a hydrodynamics system, right? It could be across domains. And that's where this becomes really powerful, is if we can have these systems of kind of low-level linked data that really function, we can start to stitch together these nodes at their edges. And that's another piece that we're working on here, is designing what does the interface to the whole collection of linked data look like, so that another system could come up and say, hey, what are the edges that I might want to match up to? Where are the edges of your system that I might want to hook to, right? So that's that demo, and I figured out we could do that. I was like, yeah, we got it. Like, that was the huge goal, is can we go from the US to Canada and just start walking their network and discovering their data on their network, and not need to worry about it. And this allows us to rebuild our caches, rebuild our indexes whenever we want. We just go walk the network and retrieve the data that they've attached to their system last night, right? Okay, so the other thing we're working on here is using this new OGC API. It was called WFS 3, Web Feature Service version 3. It's recently kind of been renamed to OGC API features. And so what we're doing fits into this paradigm. So let's look at the large lakes collection. So this is the OGC API. If we're out here, we can see, actually I'm gonna go to home just so I can give you a quick intro. We can see the conformance, so the standards that it adheres to, collections it offers, processes that it offers, and just the kind of top level administrative information about the service. So we go to collections. Here's the list of collections of features that are available from this service. We're going to go to large lakes, and you get an HTML view. There's a JSON view of this page, of course, and this is kind of the options of what you might do from this large lakes collection. And so we're going to look at features as HTML. And this is just a pageable interface to a collection of features. We could go to the next set, right? So here we are at 10 through 14. And then say we wanted to see, you know, Lake 11, we can just go in to Lake 11, right? By putting the local feature identifier into the URL. Now, what we're doing in Selfie is saying, okay, how can we use this as the technical interface to our community meta resource system, right? And exploring, so where does and this is actually technically, where does GeoJSON intersect with JSON-LD? And I only have a couple minutes left, but I think I can finish this demo. So I'm gonna go to this issue, and I'm gonna show you, so some of you will follow what I'm doing. Some of you won't, that's okay. So here's the JSON-LD playground. You paste in a little snippet of JSON-LD, and in this case, what we have is a GeoJSON feature collection with one point. And what's not normal to GeoJSON is this at context. So this is a GeoJSON feature collection that has a context at the top, and the context is what makes JSON-LD linked data. It gives you the semantic kind of decoration for your JSON keys. So this is perfectly valid linked data. We can turn it into RDF and view it as kind of typical linked data. Super cool. We can also copy this out of here. Go to, oh, I need to Google for it. GeoJSON lint. We can go over here, paste in our perfectly valid JSON-LD, and we have a point, which is a sample in Fiji, totally valid GeoJSON. That is also totally valid linked data. So when we combine this potential with this new PyGeo API, it means that the properties in this table for a feature become linked data properties. And all of a sudden we have a linked data feature API that is going to open up so much potential to have formalism around the attributes of our features that we could never achieve before. And like we figured this out yesterday that we could actually do this. We knew the possibility was there, but like we wired it up yesterday and it worked. And it's really exciting. So if you're interested in more, OpenGeospatial, GitHub.io, Elfie, the first experiment is done. There's a great engineering report. I've heard, I say that because I've heard that from people this week, which is flattering and awesome. We're really glad that people like it. The selfie is also on GitHub.io. How to get involved is here. Our entire activity plan and links to the GitHub are available. So that is what I got.
Okay, see, we got a question back there.
Hi, it's Days from Woods Hole. It's so awesome to see this presentation. I remember when you guys were initiating this idea a few years ago at ESIP. I have two questions, but I'm only going to ask one, because next door there's a session about location. And I wondered, are you able to connect to any controlled vocabularies for features that exist today, perhaps like in gazetteers, that are exposed in RDF so that you can link to them today? Or do you have to ask those communities to expose their data in that way?
I would direct you to the selfie engineering report for some answers on what you're talking about. Most of the gazetteer stuff that's out there right now is not as published as we would want it to be. So for example, the GNIS for the US is not available as nice link data. But there are pockets that we have to build on. So, but one of the biggest things here is getting the geospatial community to adopt a few of these basic technologies just to get the building blocks out there. And we're demonstrating we can do it, but we need people to do a few things before we're really going to be able to build this out. So,
and I think it helps to have, you know, this kind of thing that says this is what we can do.
Yeah.
If you build
Yep.
that out.
Yep. And we're working pretty hard to get people to move out. So
You must have watersheds in there and hydrologic unit codes and
Yep.
sweet.
Yep. Cool. Thank you.
Thanks, Dave. All right, the next talk's going to be by Kevin O'Brien from NOAA PML, who's going to be talking about integrating data with AirDAP.
Thanks, Chris. Good morning, everyone. Thanks to Chris for having me speak in the session. I'm happy to be here. So I'm going to talk today about integrating data with AirDAP. And I'm Kevin O'Brien. I'm from the University of Washington, the Joint Institute there, stationed out at NOAA PML. And I would like to obviously acknowledge Bob Simons, who is who conceived and is the primary developer for AirDAP. How many people in the room are familiar with AirDAP? Okay, there's about half. That's great. And my other role is that I'm part of the Observation Coordination Group, which reports to the Global Ocean Observing System, and I'm the vice chair for data and information in that group. And so the presentation that I'm going to lead us through will really frame around the activities that we are doing in that community. And so I should introduce that community. So the Global Ocean Observing System Observations Coordination Group. The OCG is basically kind of looked at as the implementation arm of GOOS. So they have responsibilities sort of for overseeing the activities of all these programs and networks that are observing in the global ocean observing system. And so, you know, initially that was sort of, well, let's coordinate activities and let's sort of decide things that we want to measure and that sort of thing. But in the last couple of years, there's been a greater focus on the actual data that is coming out of these systems. And I can guarantee you, you know, when we talk at ESIP, we hear a lot of technical talk about semantic web and all that kind of stuff. None of these communities know anything about that, and they're not interested in that. And in my opinion, they shouldn't have to be. You know, we should be able to build tools that allow the data from these communities to get to these higher goals, higher levels of fairness, for example, without really having to burden those communities to get there. So that's really the crux of the work we're doing within the OCG. So a couple examples, you know, we'll look at 3 different programs here that are collecting data, and they're all measuring temperature, but there's differences in the way they're providing their data. So the drifting buoy program has been around since the 70s, and they started collecting data when ASCII was the format of choice, and they are still using that today. Newer programs like Argo and the Glider program, they are using NetCDF, and they're using CF compliant NetCDF. But even in that case, you know, there are slightly different variations on the NetCDF. For example, the Argo floats are using the trajectory feature type, and the gliders are profile, which seems kind of opposite to me, but you know, that's the way they've decided to do things. So when you have 3 different sort of types of formats that a user has to access to get to the data, that means they're going to have to kind of do 3 different things to use that data, which in some cases is not good, and it does not make users happy. And in fact, I was at a meeting a couple months ago, an international glider meeting, and there was a story that there was a graduate student, and within the glider community, there's 3 prominent data assembly centers, and they all have slightly different NetCDF formats. And it was such a hassle for this graduate student to get the data from the 3 and compare them that he gave up. And that's like, oh, it's like shooting your dog, you know, that feels terrible. That's not the way we want the community to be. So how can we improve data access so that broader communities can get to this data, because the communities themselves know how to get to their own data and use their data, and they create value through papers and products, etc. But there's a huge amount of value to this data that is downstream from the communities that it's originated in. How do we access the broader communities to maximize the value of this data? And so, you know, what we're doing within OCG is we're looking at Burdette to provide us those services. So why Burdette? And this is a slide that I stole from one of Rich Signal's talks. He is an avid user of Burdette, and I saw this slide in one of his presentations to OOI, and I thought this is a great slide, so I stole it. But Burdette is basically a platform. It's a data brokerage service. It can read from many different types of files and services and databases, and also provide access, and then it provides access in a single standardized interface. So it has a RESTful API, so machine-to-machine access is enabled, and scientific analysis packages like Python, R, MATLAB, Ferret can connect directly to Burdette services and use the data. That's very easy for web application developers to create nice services on top of the data, and I'll show some examples in a little bit. And of course, through programmatic access through code and scripts, etc. But it also has an advanced search built into it. So it generates ISO metadata, documents on the fly. It supports JSON-LD. So the metadata records show up in Google search, and I'll show an example of that later. And so we're looking at Burdette as a way to try to evolve the community toward meeting these FAIR principles, and I'll also talk about that. So why Burdette again? So benefits for providers. So providers often are asked to provide their data in many different formats. It's a really hassle. It's a management burden. You duplicate copies cause all sorts of issues. So you don't have to do that with Burdette. You put it into Burdette service and it's available in all these formats automatically. The machine-to-machine services means that people can script access to it, grab it programmatically. This next one is really important because Burdette will allow you to augment metadata without rewriting files. So you might have 1,000 files from a historical data set that doesn't quite meet CF compliance or some other metadata compliance. Rather than having to rewrite all of those files, it's quite simple to just in a configuration add the metadata attributes that are missing. That way the service then provides access to the data as a compliant data source. And so that means also, because Burdette will create Bagot documentations for archiving, so we're working on this with NCEI to accept these Bagot documentation packages. That means that what gets archived is this properly documented data. So it reduces a lot of burdens for the data providers. From the user side, it's, you know, you can use the client of your choice to get to the data, because there's a good chance that whatever format you're using and whatever client you prefer, Burdette will provide data in that source, so you don't have to reformat the data. You can use machine-to-machine services to build really cool applications that meet your community's need, rather than trying to build some data portal that you want to meet everybody's need, which we know does not work. And you can also aggregate collections of aggregations. So I'll show you an example of that in a little bit. But that's a huge feature as well. So back to our previous example, instead of having to access 3 different data sources in order to get the data they want, now they have the access in Burdette. It's one simple uniform access. They can use it in the client of their choice, go to work, and they're happy. So diagrammatically, what that looks like to the user is you're in your favorite client software, you make a request to Burdette, you get the data back. What's really happening is you're making the request to Burdette. Burdette has taken that request and then translating it into whatever native request the back-end service or files are. In this case, let's say it's a database. It's making that database request, the results are coming back to Burdette, and then that gets transferred to the user. But the user is completely abstracted from what may be the original data service, data source, and that's really important. And so other clients, as I mentioned earlier, there's a whole multitude of clients that can easily can access data directly from Burdette. So this is really great for interoperability. It allows your data to be available for lots and lots of people without having to provide different formats or have them do reformatting. So here's an example. I mentioned the Global Drifter program that used ASCII data to provide access to their data. So they had one file that was data. This was up until a year ago they were doing this. And then one file that was metadata. So this is really, I mean, already it's a little difficult. It's ASCII files, metadata data, they exist in different files. So we worked with them, and you know, all credit to them. This worked for their community. I'm not saying this was a bad idea. It worked for their community, but again, broader access to these data means we need to modernize things. So, and to their credit, they're very happy to do it, very enthusiastic about it. So we modernize their workflow now to create netcdf files, which means that we have the self-describing files. So the data is co-located with the metadata, and then we put it into an ERDAP. And so, you know, with the Global Drifter program, like from 1970 to now, there's maybe 23,000 individual drifters. So that's a lot of individual drifters. It's like a 23,000 piece puzzle. You know, you have one piece, but you may want to look at the whole collection. And so what ERDAP allows us to do is serve all of that data as one collection. So you can see this is the ERDAP interface with the drifter data loaded into it. There's a graph, there's a picture with all of the drifters, but I mentioned these RESTful services, and this is really where the power of accessing ERDAP really comes in, because you can build higher level tools on these data services. And so this is a live access server from NOAA PML, which is actually developed within my group. We've put this on top of ERDAP, which allows us to then sort of dive into the data and look at it. And so you see here the whole collection of drifter data. I think this is the first 4 or 5 months of 2018 displayed right in front of you. Rather than individual files or having to download, you can look at the collection, which means you can start drilling down, looking at property plots of individual drifters or in context with other drifters. So this is really a great way to view the data, and this is all possible because of the RESTful services that are on top of ERDAP. So I said they don't know anything about semantic or JSON-LD, and they don't, but with ERDAP, if you have your data in ERDAP, that means that it automatically, as I mentioned earlier, supports this JSON-LD metadata. So in a Google dataset search, if you search for global drifter data, you'll see in the results, this is probably about the 4th result that showed up. I scrolled down a little bit on this to take the picture, but you'll see the data which links right into the ERDAP services. Now, I didn't do anything to get that in there. I just put it into ERDAP, and it was discovered about a week after that. So a little scary, but it's good. So I just wanted to point out another institution that's widely using ERDAP and doing really amazing things with it is the Irish Marine Institute in Galway. They have something called Ireland's Digital Ocean. So you see here the Irish coast and the different platforms that are surrounding it. And if you click on one of those platforms, what comes up on the left side is sort of a status and the parameters that platform is measuring and their values. This is all driven by ERDAP in the back end. So that click on the map provoked these calls to ERDAP. It does GeoJSON, it returns JSON, it returns Google data tables for charts automatically. So natively in the client, you can draw these charts very easily. So this is one example of how it's really effective using ERDAP services to provide access and more value to this data for users that may not be familiar with the community or the process of that community. And they have several dashboards, you know, one for each of those moorings where you could then go to and get more information. And all this is based on ERDAP services. So finally, I'd like to talk a little bit about ERDAP and FAIR principles. And, you know, FAIR principles, I'm sort of learning about. They aren't, you know, in the ocean community, the FAIR principles are sort of looked at as a way to improve interoperability, but they're not designed for the ocean community. You know, they're designed for the digital community. So they're pretty abstract and generic, and there's lots of interpretation to those. So how do we meet these FAIR principles? And we think ERDAP is a really great way to do that. So in terms of findability, you know, ERDAP, as I mentioned, can easily augment the metadata with missing elements for compliance. So that helps with the discoverability. It generates ISO metadata documents on demand. So this is harvestable. So we already have processes in place where NCEI is harvesting ISO documents from ERDAP to put into data.noaa.gov. In terms of accessibility, you know, you've seen how ERDAP will provide access to data in multiple formats. It has these RESTful services for machine-to-machine services, which is incredibly important for interoperability. And it provides a platform on which you can build these data-specific tools that really meet the needs of communities rather than trying to build this one sort of size fits all. I'm going to skip the I for now. And then in terms of reusability, of course, it supports archival, which is incredibly important to ensure that the data goes to the archive centers and is is saved for future generations to use, and DOIs are, of course, an essential part of this reusability, or at least citability, so that people get credit for their data. And then again, in terms of reusability, it supports these metadata conventions like climate and forecast and JSON LD. And I feel like all of those three sort of roll into the interoperability aspect of FAIR. The interoperability list of FAIRs, it's a little confusing to me because it's kind of recursive. It refers to itself, but I think all of these together fold into improving and evolving these communities towards meeting higher levels of FAIR strategies, really with only serving the data through ERDAP. I mean, it has to be well documented, of course, but putting the data into ERDAP really helps move people along this way quite a bit. I think that's it. So thank you. Any questions?
Any questions, Ed?
Two questions here. This is Ed from the JPL PODAC. One of them is really simple. So for your ERDAP servers, anything on the oceanographic GTS in ERDAP?
Yes.
So all like the ship observations?
Yes, one of the projects that I technically oversee is called the Observing System Monitoring Center, and we've put the entire GTS collection in ERDAP. So any ocean observations that are being collected on the GTS, we have through ERDAP services.
Excellent, excellent. A second question. So is there any capability in ERDAP to link those in situ points, say from drifters to satellite records that are coincident with the drifters?
No capabilities that I'm aware of at this point. I'm not sure how that would work.
Yeah.
It's an interesting question.
Yeah, that matchup service is sort of like the holy grail.
Yeah.
Satellite folks.
Yeah, that would be something.
I had one quick question. Do you support any of the OGC protocols? Like
Yes,
WCS?
OGC, yes, WMS is supported, yes.
WMS, but not WCS
And
or
WCS,
WFS?
not WFS, I don't
Okay.
believe, but WMS, WCS, yes.
Okay, thanks.
Yep. All right, thank you.
All right, now I'd like to introduce Namrata Malarote, who's going to be talking about the multi-mission analysis and algorithm, multi-mission algorithm and analysis platform, and some of the things they've been doing with respect to integration inside MAP.
Thank you, Chris. So yeah, I'll be talking about MAP, and more specifically, I'll be speaking to the centralized MAP API. But before I begin, I would like to acknowledge all of the members of our team and our collaborators, because this is a big effort. And as you can see up there, we have collaborators across NASA's Goddard, one being Chris, and Marshall Space Center, Development Seed, University of Alabama, and we've got AST, NASA headquarters, and ESA. So this is a joint collaboration between NASA and ESA. And I have wonderful team members from JPL, and everyone's very hardworking, and this is going to be a very fun project. You may have met some of other members of our teams, like Amy from Development Seed here at ESIP, and Sojen. So yeah, now I'm gonna dive in. So MAP is a new paradigm for delivering open science. So it's a cloud-based virtual environment, which is targeted towards helping scientists discover data, process it, analyze it, and share it. So NASA and ESA are partnering, each supplying their technical and scientific expertise along with some critical data sets. So the primary goal, as I mentioned, is to enable the researchers to provide a version-controlled algorithm development platform for them, where they can have tools to support co-located data and processing resources. And at the same time, we want to provide them a wide variety of data in the same coordinate reference frame to enable comparison and analysis, data evaluation, and data generation. And through this collaboration, we also want to address intellectual property and the sharing issues related to collaborative algorithm development and the sharing of these data and the algorithms. We want to be able to identify best practices for interagency collaboration and develop a better understanding of each other's programmatic processes and objectives and abilities. So these are some of the elements of MAP. So we've got the ADE, the algorithm development environment. So we're using Eclipse Shea and Jupyter Lab plugins to facilitate this. Then we've got the MAP data store where we will be hosting the data products that are produced from these algorithms. There's the DPS, the data processing service. So we are using this to run code at scale by using HiSDS, which is a software developed at JPL. So we can scale out the jobs using Amazon Web Services. The MAP algorithm store is going to hold all the algorithms that scientists have said, okay, I would like to share this with other people. So this will be a catalog for that. And we've got visualization, fast browse, of course, authentication and authorization, the data analysis service, and the MAP API. So this is a very high-level overview of what all the subsystems look like. So now when you see here, you can see the different layers. All of the client-side applications sit on top of the MAP API, and under that, you will see all of the REST services corresponding to the different components. And further down, you can see the infrastructure. So how are we handling interoperability? So we're following OGC standards for our visualization services. So we're using WMS and WMTS. And for the process side of things, we're using WPS. We're using NASA's Common Metadata Repository and Unified Metadata Model for enabling the search and discovery of data sets. And we wanted to have a common API for all of the different components to interface through, which is what we are calling the MAP API. So this is a common set of web services between NASA and ESA platforms to adhere to the open standards. And this is integrated with MAP's CMR and the dynamic tiling API and the data processing system, which is HiSDS. It's complemented by a Python wrapper library that we have, the MapPy, which can be used to invoke the different MAP API endpoints. And these endpoints are broken down by components. So this is just a screenshot from our Swagger API. So I'll be diving down into our different endpoints that we're supporting. So starting off with authentication, we allow like registration of an account to the MAP API and the ability to verify your account through a verification code sent to your email, and the ability to log in using access tokens. Then we've got data catalog and discovery. So we want the scientists to be able to find the collections and get the collections by ID, discover which granules are available for these collections, and get a specific granule information by ID, and so on. Then we've got the MDS, the data store. So we want people to be able to upload their granules, download them, remove them from the MDS if they'd like, or get more information about the granule by the ID, by the ID, and get the capabilities. With the MAP algorithm store, we want people to be able to search the algorithms and get more information about a specific algorithm, saying, what are the parameters for me to be able to run these algorithms? And we want to be able to register these algorithms when a scientist is ready to say, okay, I want to share these with other people. And the deregistration of an algorithm. On the algorithm development environment end, we want the end users to have the ability to work on their code. So we want them to be able to find their repositories and load them into Eclipse Shea. And so you can find workspaces that may have been that are your own or shared with you by other collaborators. Getting workspace information, removing a workspace, loading them in, saving your workspace, and then building this workspace into a container, because we are containerizing everything that you are developing so that it can be run at large scale using the DPS. So with DPS, you want to be, now that the algorithms are made available to you, you want to see, okay, now which jobs can I run? You can get a description of a job, which is essentially the parameters. Then you can submit them. So you can queue up a job by submitting the algorithm and providing your parameters. You can get the information, the current status of the job. So you can keep track of, is it still started? Has it already finished? And once it's finished, you can get the results of what was produced from your algorithm and where the data is staged. We've got fast browse. So you want to be able to get capabilities, feature information, and tile information about the static tiles. And for on-the-fly map or tiles, you want to get the map and the capabilities. With data analysis, we would want to facilitate the sharing of the data to a group. So from L1, you want to be able to run ARD generation and load the RDDs into Apache Spark and present a visualization via web UI to the users. So I specifically have been working on the algorithm registration and the data processing side of things. So this is just a brief overview for you of what that process looks like of algorithm registration. So from the algorithm development environment, when you're ready to share your algorithm, you would like to say, okay, register it so that it is visible and available to other users. So it makes a call to the map API. This automatically triggers a build. We are using GitLab to do our continuous integration. This ends up packaging that code bundle and uploading it to Amazon's S3. We have a dedicated code bucket to host all of the different code bundles. And then the metadata related to your algorithm, which is going to be who is, information like who's the owner, again, what are your parameters? Do you have any restrictions on what values are allowed for those parameters, things like that. All of that gets stored in the algorithm interface definition within HiSDS. Now, once that is done, we want to be able to notify the user saying, okay, your registration is done. So now it's available for you to actually run in the data processing system. So alternatively, you can search for existing algorithms. And once you've done that, you can submit to get more information. So now I'll dive more into what actually happens in the job execution side of things. So when you're ready to execute the algorithm as a job, you're going to make a call with the algorithm's ID, with the list of parameters. When you do that, it validates all of your inputs against what we had already registered regarding the metadata of the algorithm to validate whether or not this is a job that can be run and whether or not your parameters are correct. After that validation, it gets queued up into the job management system. Now, the auto-scaling, we're using auto-scaling groups. So the compute nodes are going to pick up your jobs, execute them. Once that is done, and it recognizes the products that have been created within the work directory, those data sets are uploaded into the products bucket. And the metadata related to the product that you have created also gets indexed into the metadata catalog. So the metadata catalog for the jobs themselves and for data products are two separate things. Once you can poll to see what the job status is. Once it is completed, you can get the job results. So this gives you information about what is the location of your product on the S3 bucket itself. And we're working on kind of better visualization. So hopefully maybe we can display the product that has just been created instead of just giving you a link. But right now, the way it is done is it gives you a hyperlink. You can click on it and you can view your products in the bucket and download them. So challenges. First and foremost, I'll talk about authentication and authorization. Since this is a collaboration with ESA, we need an authentication system to validate across organizations, right? And we would like it to be a single sign-on. So we're using Syncope for identity management. And the challenge here is propagating authentication across all of the applications and all of the different layers. So we've got Syncope, we've got Eclipse Shea, we've got the DPS, which is HighsDS, we have the MAP API. Now, we don't want people to be validating and logging into all of these different services. We want it to be a one-time thing. And we want to be able to get fine-grained user activity, right? And we want access control over the AWS objects. And we want to be able to track costs and the user activity on the MAP platform. So we need to propagate the login to all of these different levels. So the solution that has been employed is using the CAS framework for single sign-on, using the proxy authentication. So this was worked on by a couple of people, including Brian Sartorius. So they've done a great job of accomplishing this and propagating the auth to all of the different layers. Now, using Jupyter Lab plugins with Eclipse Shea. So developing the ADE, right? So Shea is just providing you the workspace and it does the user management. But Jupyter is where your actual workspace code is hosted, and that is what interacts with the other map components. So getting the Jupyter Lab plugins to work within Eclipse Shea has been quite a challenge. And from JPL, Maya and Elizabeth have been working on this. The usability of the open source technology when it comes to these plugins has been a little challenging. So they discovered that it had embedded constants and paths, and this made the integration very hard. And this makes testing and deployment not as smooth as we would like. It requires the rebuild of the workspace itself. So we need to do an entire Docker rebuild versus having to do a simple local just installation of that plugin. And with Shea, which has just been released in March, all the features that have been advertised are not currently available. So it requires some extra development efforts on our side by our team. The good thing, however, is with open source, it is a very active community. So it is very helpful in the development process for us to get answers or get some more expertise. Now for conforming to the UGC specifications, when it comes to the different components, for example, the DPS, getting a right fit of which WPS operation should be mapped to what already available API endpoints are available readily from the DPS has been slightly challenging and making the responses OGC compliant. And then when it comes to algorithm registration and the algorithm code, right, for MAP's perspective, they are two completely separate concepts. However, I have been working with the DPS, HiSDS, for a while. So in the development process experience that I have had, the commingling of these two concepts is very common. It's thought of as one thing. The description of the algorithm and the code itself is considered, the thought process is it's one and the same thing. But separating that here and decoupling it and making it explicit, that is not a very big challenge, but it did take some standardizing and conversation and say, okay, we are going to separate these two out. We are going to consider the Docker environment itself completely separate and not have that linked to the process of building up the code. So yep, those are some of our challenges. We are in the pilot stage, so work's still in progress. And that is it. Thank you.
Yeah, I have a question about your algorithm registration and storage
Sure.
process. When I think of algorithms, I think of theoretical basis documents. I think of source code and executables.
Yes.
So what is registered and stored?
All right. So when it comes to okay, let me separate this out into three things. One is the actual environment that you would like to facilitate so that your code can run. So for this, we are using a base Docker file that is built at the Eclipse Shea level, which would have all of your libraries and whatever plugins you might require. So that we use as the base. Then using your code, so whatever you have on, say, GitHub, we install your code on top of that base Docker file layer. So that becomes your executable. Then separately comes the algorithm definition. So it is up to a user to define, okay, I know I am the developer of this algorithm, so I know what the parameters are. So here, because we are using HiSDS, we declare this as a key value pair. So we would like the user to tell us what your list of parameters are and how they are to be used, right? Are they positional arguments to your script? Are they something that you are piping into a file and cracking it open and using it in your own script? So that becomes the algorithm definition. And then we have the algorithm code.
In addition to what Namrata just mentioned, I think it's the Marshall half of the team is working on an algorithm publication tool, which has that, text and description, in a human readable form.
So related to that, how do you manage the version? Do you have a workflow or process to actually review?
Yes. So we, from our side, do not review the versions. It is completely up to the developer. But yes, we do like to have version controlled instances of your algorithm. So during the registration process, it creates a unique identifier for the algorithm itself. So it would be whatever name you specify, and appended is the version. So the version right now, we are determining based off of the branch name. So if you're developing using something like GitHub, and you want to make some code changes and add some new features and put out a new version, it means that you're using a different branch. And we're just pulling that information, and we're essentially, you can think of it this way, we are stamping the algorithm with different versions So when we build your code, it will be corresponding to whatever improvements you've made. So you would pick that and run the jobs.
Thank you very much, Namada.
Thank you, Chris.
And for our last talk of the morning, I guess it's okay, so Davin's going to talk about Sparrow. I got the message about it having to be PDF, right? Yeah. Okay.
Okay, thanks for the opportunity to talk in this session. So kind of at the smaller end of the institutional size spectrum, I'm going to talk about some ways we are trying to bring together geochronology labs into the kind of community data system fold and how we're approaching that problem. So this will be kind of a conceptual overview, but hopefully it'll present an interesting way to do this. So I come from a perspective as a stratigrapher and structural geologist, so I'm going to kind of start in my comfort zone, which is just starting with the fact that geologic time is a very fundamental concept and obviously a very important one in all sorts of fields. And geologic time is defined throughout geologic history. So on the right there, or the left, there's a GSA geologic timescale, and on the right there is a stratigraphic column of the Grand Canyon region of the Western US that is basically all of the packages of rocks are defined by geologic interval boundaries, or they define the geologic interval boundaries. And then that goes forward through geologic time. And basically the geologic time scale, all these boundaries are actually boundaries between packages of rocks somewhere on the globe. So that's kind of the starting stratigraphic framework for relative geologic timing. Everything breaks down to layers of stratigraphy. And in the stratigraphy community, we've started building kind of community data systems to manage this data globally and its intersection with the geology that we see on the surface of the Earth. So this is one example of that type of system. So it's MacroStrat, which is basically a stratigraphic column for different locations on the planet, compiled from USGS literature and other sources elsewhere on the globe, and that kind of intersects with the geologic map that has the same units. So we have kind of a spatial and temporal index of, in this case, an area in North America, but ultimately we're hoping to go around the globe with that. And with that comes a relative set of time-ordered geologic events, if you will. But one of the conundrums that's been with us from the beginning of trying to do things with geologic representation of time is that to do anything global that's not within a single stratigraphy, you really need to reconcile relative and absolute time. So this is just one of many examples of studies that kind of synthesize global data. So this is actually a temperature data set with a very aggressive logarithmic scale on the bottom. So it's starting from years on the left and going backwards in time all the way to 60 million years before the present, basically showing us that we were hot before and we cooled down and we're getting a lot hotter again, but we've been back there. But these are on the top axis, there are geologic time intervals that are, again, defined somewhere on the globe by a package of rock. And then on the bottom, there are absolute time units. And somewhere in the middle, there are all these global data sets that are hung between those two axes. And this is a lot of work to do. And the most common way to get this absolute time is this broad field of geochronology, which is basically the ability to date rocks, some rocks, the rocks that have the appropriate minerals and isotope systems within them. And then you're able to create absolute ages that are stunningly accurate for individual geologic events. So this is a classic example of a 548 million year old ash bed that there's no scale on this picture, but it's about 2 centimeters thick. And the zircons within this rock give us a age of 548 million years, which is just before the Precambrian Cambrian boundary. So we pinned this area of southern Namibia to exactly that point in time. And this has been hugely successful in pinning the timescale of geologic history together. But one thing we would like to do is bring this into the ability to be analyzed in aggregate, like we're doing with the stratigraphic data, and be able to look at the collection of geochronology ages together. And so, kind of assessing how we would do this, we can start digging into what does this data look like in the first place. And so geochronology labs that deal with different isotope systems have fundamentally different data with rich analytical data coming from a series of mass spectrometers and other machines, and also rich contextual metadata. And these are being compiled by specialist workers in geochemistry with no data management expertise. But just to go through kind of a generalized workflow for one specific laboratory type, this is for an argon-argon geochemistry lab. And so you have metadata about the location where the sample was collected at the top, and what type of sample. Did it come from a volcano or from a subsurface pluton? And then what type of rock it is, the individual sample. And then within the rock, what type of mineral grains were analyzed. And then there's a whole sequence of analytical steps, including irradiation in a nuclear reactor and fractionation of the sample. And then there are different gas parameters on the mass spectrometer. And then finally, an interpretation of an age by an analytical worker. So it's very rich data. And the data has a lot of metadata associated with it that isn't always fully tracked through the process. But it's not very big data. So it's the workers in these labs are like, oh, this data is very big, but their whole archive can often be 4 gigabytes or 20 gigabytes of data. But it's, the complexity of the data is really the stumbling point here. And so what does the data system look like then is the question. And this is kind of unfair because some labs are actually moving beyond this kind of framework, but for most legacy systems, and most labs have a huge legacy archive spanning decades that is essentially like in different versions of Excel files. And this is an example from one of the major detrital zircon geochronology labs in the US, and it processes hundreds of samples a year for many workers. And these Excel sheets actually embed the full model used to calculate the age as well as the data, but none of the sample metadata information. They're very large and complex Excel spreadsheets with macros that are about 80 megabytes a piece. So it's maybe not a modern system that makes you comfortable that you're tracking things correctly. But it works operationally, and that's kind of where they are. So kind of from this framework, attempts have been made to create a community data system within the geochronology community. So this is geochron.org, which is part of the EarthChem project. And its intent is to aggregate data from geochronology labs and bring it together into a central endpoint that can be used by other workers. But it's kind of designed in this Excel paradigm. So it involves things like manually uploading spreadsheets that you have copied the columns into their format. And then upon download, you are asked to download spreadsheets or XML that works with the suite of age calc tools that have been designed by this organization, which are often not the ones in use in the lab for their mass spectrometer data. And there's not really a searching or filtering capability. And crucially for workers outside of the community, it's focused on analytical data. So it will give you, different age steps and very detailed chronology data about how you are making the measurement. But the worker who downloads the data is still asked to make the interpretation of the age. So it's really only usable by expert workers because I couldn't go in there as a stratigrapher and say, I don't know anything about uranium lead geochronology. What's the age of this rock? You would have to do some sort of analysis to figure that out. So these types of limitations have limited uptake because it's essentially more of an archival facility for data, and it doesn't provide a lot of exposure outside of the community. So we are actually trying in this EarthCube grant that got funded a few years ago, and I'm a postdoc on this grant, a somewhat different approach. So this grant was actually funded to a consortium of geochronology laboratories around the country. So the 4 major ones here, plus a few smaller labs that don't have logos. And basically, we want to build a community metadata system, but emphasizing how this system fits into the within lab workflow for geochronology labs. And so that led us to building a new piece of software that we are calling Sparrow, which is just a name with no acronym. But ultimately, this is a data management system for labs that also has an infrastructure component. And so we're early in this process. But so I'll kind of present the architecture of how this system fits into the overall picture. And so this is kind of the data infrastructure viewpoint into the system. And so, you know, from the viewpoint of somebody like Macrostrat or, you know, somebody outside of the geochronology community, we have a target, which is we want to understand ages within the Earth system. And then we have a bunch of complex pipelines to produce data, which are ultimately geochemistry labs, which have their own internal systems. You know, some are using Python data reduction pipelines, some are using things in Java or C or MATLAB, and then putting things in spreadsheets. And like ultimately, they have a legacy archive of data. And what we're hoping to do is add kind of a interface on the end of that pipeline, whatever it is, that maps that into a common format that can then be accessed by consumers outside of the geochronology community. So then zooming in on this kind of Sparrow blue box at the end of all of these lab pipelines, we can start looking at more what it is from the lab's perspective and what this piece of software actually does. So it really has 2 components. The first is a structured data store, which is both a relational database, in this case PostgreSQL, that holds geologic context data, project metadata, and structured data for a subset of the data within data files that's relevant for indexing and use outside of the community. And then it also holds the analytical data in its original format as a file or whatever it is, and links it together with that structured data. And then there's also an interface side, which provides a few different ways to access this data. So it provides a standardized API on top of the data, which can be used to query this lab and pull data into different archives and Earth models or whatever other use is envisioned. And then because we're already building a web stack for this, we realized we could provide things like a web presence for the lab with data-driven visualizations and summaries of the data that would be useful just for understanding what this lab has to offer. And also we can provide some basic components to manage metadata. So not actually analytical data, but data like projects, links to publications, whether data is embargoed, and that sort of thing. So we're trying to design a product that is usable for multiple labs that are using different types of geochronology. So we're trying to design something that is extensible. So it can be used at labs that are doing different types of geochemistry and can be customized both in its database design, its API endpoints, and how its front end looks and operates while still maintaining a common core. And then we wanted to decouple the different parts of the application. So one thing that we're trying to do is if the funding for this or the development on this evaporated and labs were using this system, we're trying to make a system that if it disappeared, what they have is a PostgreSQL database with all of their data instead of a collection of Excel sheets. And then they'd just have to figure out a new way to access that database, but it would be a structured data store as opposed to the unstructured one they currently have. And then we're also trying, as part of that, to make it lightweight. So to knit these components, PostgreSQL, a React front end, and all of that together with a minimal amount of glue code so that we can, not have to maintain a large software system beyond the very powerful components that it integrates. And so the nice thing, we're starting to do this extensible framework. The nice thing about being a collaboration between labs is we have a lot of different test cases immediately. And so we're basically building an application that can be modified for different labs. And I like to think of this as like a WordPress, but geochemistry data instead of your blog posts, where you can have a common core of how this data is represented, and then you can slice and dice it in all different ways. So this is a few different views of the data. The first one with the rainbow on it is just kind of the default that comes out of the box with no data in it. And then for different labs, we have one lab has done a very good job of tracking their location data of their samples already. So we can foreground a very nice map that shows how many places they have measured their data. And then another lab has none of that data tracked, but they have a humongous collection of samples. So the Arizona Lasercron Center has, I think we've ingested about 10% of their archives so far, and it's 84,000 ages across the Western US and across the world. So, this is a huge potential archive if we can get it to have the proper metadata. And then more on an operational side, how this actually works. Basically, what the lab needs to provide to get this system working is an import script that can figure out their data file format and move it into a normalized schema. And there are helpers within the Sparrow libraries to assist with creating this import script. But the important thing is that only a subset of the data needs to be normalized, whatever needs to be exposed to the public or exposed to manage the lab's data. The rest of the data can stay in its original data file and can, the import script can be modified if needed to move more of the data into the kind of public-facing realm. But it's meant to be flexible and easy to get started with. And this normalized system that for the analytical side of the data at least will basically be a hierarchical data model, which is pretty common to other systems that have tried to represent geochemical data, where single measured values are represented as one data type with their meaning given outside the system by a vocabulary. And then those are integrated up into analyses at single points in time, and then measurement sessions that are coming from the instrument at the same time, and finally to sample and geologic context and those external attributes. So the hope is this is adaptable to all types of geochemical data. And part of what makes it adaptable is that it's vocabulary controlled. And what we're trying to do here is not presuppose a vocabulary or a set of data types that will be used by labs to manage their data. Often labs have very, very specific internal data types that mean, exactly what they say it means and which collector they measured it on, and, have different impedances between the collectors and all of that. So what we're doing is creating a lab-specific vocabulary that is basically under their authority, and then the ability to map that vocabulary to more community standard vocabularies for use in the API. So the idea is the API could return either the Arizona Lasercron vocabulary or things that are mapped to the EarthChem vocabulary, which is focused on analysis. It's focused on isotope ratios and things that you can use to calculate ages, or some interpretation-focused vocabulary, which Sparrow will create probably a basic version of this that will say, is this an igneous formation age? Is it an age that we are confident about? Is it an age that we think might need to be reanalyzed? And just kind of these things that will let somebody outside the community understand what the value of this data is. And then kind of the last component of this, and part of what makes this really a sell to the labs as a tool, is the ability to do project and metadata management within a web interface that sits atop this API. So we're able to build a set of pretty basic web forms and things to ultimately manage aspects like embargo, which is very important when you're trying to put your whole data archive on an online accessible platform. Also links to publications and researchers, samples grouping into projects, and eventually, hopefully, facilities to help with linking IGSNs and other data products for kind of bringing the data to the community. So this curation step is something that really has a lot of people excited, it seems, because the ability to track publication metrics and stuff like that is valuable to any lab. And just to kind of end on the project status, basically, we have started this project in the fall of last year, and we've deployed initial instances at several labs with kind of a testing data that we're not doing too much with until we get the bugs worked out. And then we have testing instances on several other types of data outside of our set of labs. And we've run one workshop in May of this year where we began discussing design and implementation challenges at different types of lab. And that's pretty much it.
Thank you, Davin.
Thank you, David. Yeah, very interesting talk. Apparently, yeah, this kind of data is really different from the normal earth science data. Although you say, well, it's not big, but it's very complex, right? So I'm not sure. So perhaps the uncertainty is definitely one of the issues you also consider for this data. Do you deal with those kind of? So because this uncertainty is not only for the data itself, could be also from the interpretation from the scientists, whatever,
right,
who collect it, right?
Yeah, so this is a huge problem, and this is one that geochronologists have dealt with very carefully and with very complicated and informed models of uncertainty. And one of the issues actually with the uncertainty is those uncertainty models are often not approachable outside the community. When you want to understand, just like if we're going to put this on a plot or use it in a model, we need ultimately an error bound that is easily interpretable as one set of errors. And so part of the struggle with this is being able to say, please give us the best error bound. And that's actually why in a lot of cases, in fact, I believe why geochron.org made the decision not to foreground the interpreted age data is precisely because of the issue of different people can make different interpretations. And they kind of said, well, we're not going to worry about this problem because it's a huge problem and we don't want everybody to just interpret get the age data and think that the interpretation is like a golden stamp on the age and make all sorts of assumptions with it. So, that's an ongoing problem, but I think having the rich metadata will help with solving that over time.
Hi, Stace in the back. Really great talk. Really great to see a tangible outcome of EarthCube that I can bring to my institution. And I wanted to kind of just have you talk about so a lot of the scientists that build these sort of databases using the Excel spreadsheets, for example, they lack the capacity to be able to reach the database, administration that this requires. So how, I try to do this at my institution, how can you help the long tail scientist that's using Excel be able to implement this database and system that is, involving the database?
Right, I think there are two parts to that answer. The first part is we're trying to make this system as easy as possible to spin up, just to get an instance that works and you can start interrogating the database and understand what it does is because of things like Docker quite easy to do now. And I think that hasn't been the case in the past. So that is a step forward that we're able to make. I think the other part of it is part of why people are using tooling that is maybe not the correct database tooling that we would conceive of in these labs is partially because they don't quite know exactly what tooling to use, but a lot of geochronology labs invest a lot of time and energy into their data system. It's just often a lot of energy that is on directions that may not be long-term fruitful and you know, kind of community endorsed because they're kind of rolling it on their own. And I know, for example, one of the labs we're working with has 2 in-house databases, one of which was provided by the mass spectrometer company, and the other of which was rolled their own by their lab researcher. And it's been a reasonable system for moving their analytical data around, but they do in that particular lab have a lot of expertise in databases that they could use within a system like this. And certainly if there's enough of those labs, not every lab will be like that, but if there's enough of those labs, then it can become more of a community internal thing where people are using the tool internally and developing resources to move that ahead. So that's kind of the hope there. But that's why we have these big like user facility labs on our grant, because they have a lot of resources that smaller labs do not.
Do you see any promise for cloud-based databases to kind of depoliticize where the database is and perhaps for, provide more community collaboration?
Right, yeah, so there's a second level to this whole system that I didn't really talk about here because I've kind of been focused more on like getting the lab's internal data together. But whenever you start talking about then like how is the community going to access this data, ultimately you realize, well, the community probably doesn't want to pull it from every single lab. So there's a second layer of community database that's almost a requirement in this case, but what we're doing is essentially making it easy for that community database when we design it. Maybe we will design it, or maybe somebody else will design it. Maybe the architecture will be similar to what we've presented here, or maybe it will be different. But we're making it easy for that database to pull the data and just get up and running with all the data that these labs have quickly.
Great, thank you. Let's thank all of our speakers.